What is up, you guys? So in this video, we're going to tackle an instance of a combinatorial optimization problem that is the so-called knapsack problem. Now, indeed, there's many variations on the knapsack problem, such as the 0-1, the fractional, bounded, unbounded, quadratic, and many others. In this one, we're going to keep it simple so that we see how to approach this problem using both dynamic approach and a convex optimization approach. Now, as we did in the previous lecture, which was the first lecture of my convex application series entitled the transshipment problem, as we did there, we gave an example and we learned through this example how to implement it on MATLAB, how to formulate a convex optimization problem, which was in the transshipment problem, a linear program. We're going to do the same thing here. By the way, this lecture is based off a comment by Noelle Nathan, where she asks if I could generate a video on the knapsack problem. And here it is. So really, if you have any suggestions, I will take them into account. For example, Bula Moore, she asked about the traveling salesman problem. And I will be taking this into account in further lectures. Carrie Rowe asked about some connections with economics. I am thinking about that and I will address this in future lectures. Don't worry about that. Okay, so congrats, Noelle. This video is based upon your request. So in this lecture, we're going to see what the knapsack problem is, how to take a dynamic approach to solve this problem on C++, for example. We can implement a code to solve the problem as such, and how to approach this problem from a convex optimization point of view. For that, I'll be using MATLAB to see the solution over here. Okay, so without further ado, let's get started. Well, the best real-life example to give on this problem is to imagine yourself as a thief. Well, I'm not going to take this scenario into account because I imagine all of you guys are adults and you're not going to rob a bank or you're not going to break a door one day. So I'm going to give you another example. Imagine you find yourself in a shop of valuable items, right? However, you only brought with you a knapsack or a bag or a duffel bag, put it that way, with a certain weight W. So this is you, let's say, and this is your knapsack. Not that good at drawing, but bear with me. And it has a certain capacity, or it could fit a total weight of W, okay? And you're in this shop with valuable items, and you've got the following 6 items, all right? Now, imagine that each item has a certain value, for example. So this guy has a value of $175, $90, and so on. I'll throw in some random values. So those guys are the values. On the other hand, each of those items have a certain weight. Let's say this guy weighs 10 kilograms, for example, or occupies 10 centimeter cubes. This guy is 9, and so on. So you're in this shop, and your bag or knapsack doesn't fit more than, say, a maximum weight of 20, okay? So you're allowed to pack in, let's say, items 4 and 5 and 3 so that they sum up to something less than 20. So your objective here is to pack in as many items as possible in such a way to maximize your total value in such a way that the knapsack doesn't break. So in such a way that the total weight of the items remain less than or equal to 20. All right. Now, a solution to the knapsack problem will indicate which items should be added to the knapsack, right? The solution can be broken or decomposed into decision variables. So if I indicate or if I attach to every item a decision variable, x1, x2, down to x6, where each of those variables are binary, right? So it's either 0 or 1. That means you either pick it or not. Then we can formulate a certain optimization problem here. So your problem will be to maximize the total value in your knapsack subject to the weight constraint. The total weight in your knapsack remains less than, and of course the constraint on your decision variables that they should be binary, right? So throughout the years, there's been a lot of approaches to this problem that you see. Now, first of all, this problem is a combinatorial optimization problem. That is, you've got a type of problem with a certain objective, and the problem consists of finding the optimal solution through a discrete or finite set of objects, right? So here we've got 6 objects and we decide whether to pick them or not. This is a type of combinatorial optimization problem. Other types of combinatorial optimization problems could be the traveling salesman problem, where you've got a list of cities and the distances between each pair of cities. And you ask yourself this question: what is the shortest possible path that visits each city and returns back to the original city? Thus, you're a traveling salesman. Another type of combinatorial optimization problem, other than the knapsack and the traveling salesman, is the minimum spanning tree problem, where you've got a graph which is connected with some conditions, of course, on the graph. Each edge of the graph has a certain weight. So let's say this is a graph. Over here, you've got this, that is connected here. What I'm drawing right here is a type of undirected graph, right? There's no sense. So I can go from A to B with a weight of 2, and I can go back from B to A also with a weight of 2. So the minimum spanning tree is a subset of this graph without any cycles and with the minimum possible total edge weight. It is a spanning tree whose sum of edge weights is made as small as possible. This is also a type of combinatorial problem. Since you've got a discrete set that are the edges, well, they're the ensemble of edges and vertices. It's discrete, it's finite, and your problem here is to find the subset of this graph with minimum possible total edge weights. Okay? Of course, by preserving the property of the graph that is connected and should have no cycles, right? Now, combinatorial optimization is one branch of mathematical optimization that is related to other fields such as machine learning, graph theory, artificial intelligence, signal processing, and many, many others. Well, back to our problem over here, we've got this knapsack problem. We can see it as a combinatorial optimization problem, and hence we can propose some greedy algorithm. Well, in this case, the greedy algorithm is optimal because if I want to come and solve this problem by just looking at it as such, if I go ahead and pack the item 6, well, the total weight is 20, which is accepted. But the total value that I packed in is 200, right? So 200 would be my total value that I packed. Okay, 200, can I do better? Well, yes, you could do better. So this is not the optimal solution. So picking the 6th item alone is not the best you can do. Let's say this is person A that chose this strategy. Well, could B do better? Let's put individual B over here with his knapsack, and individual B proposes the other approach. He proposes, oh, well, since 200 is okay, but it's the only item I could pick, well, I'm not going to start with 200, I'll start with 175, because, I still have some margin left. It's 10, right? So let's pack in item 1, and I'm left with what? If I have the same knapsack capacity, 20, after packing item 1, I'll subtract 10 and I'll end up with 10. So I could still pack in 10 kilograms, for example. So item 1 is not there. Let's go to the other valuable or second most valuable item. Well, of course, item 6 will not weigh in because 20 is larger than 10. Well, what is the next item that is the most valuable and still could fit in my knapsack? Well, it's 2. Let's pack in 2. Now I have a total weight of 10 minus 9, which is 1. So 1 is left. 1 kilogram I could still pack in. Okay, 1 kilogram. Well, what is the total value of my knapsack at the moment? It's 175 plus 90, which is 265. So the total value I have right here is 265. Over here it was 200. Only 200. Okay, well, could I pack in some more? Well, up till now I packed in more value than A. B packed in more valuable items than A. Well, could I pack in some more? Well, let's see. I still have 1. Well, 1 is gone, 2 is gone, 3 I could not pack in, 4 I could not pack in, 5 I can pack in. And my knapsack right now is saturated, right? And the total value at this point would be 265 plus 10, it will be 275. Okay, well, what I did right now is some sort of greedy algorithm. Let's propose something else which is more concrete. Before I go into the optimization problem in hand, I'm just showing you other approaches to this problem. So this is one approach, a greedy algorithm. So before I go into the convex optimization part of how to solve a knapsack problem, I'm going to show you how to approach this problem from a dynamic programming approach. Basically, what dynamic programming means is that it's a type of optimization problem over plain recursion. So whenever you see a recursive solution in your problem, you can see a recursive pattern in your problem that, more or less that you could, solve, if you could pick one item, which we just did with person B. So person B picked item 1 and then repeated the same process over items with one being eliminated and so on. So there is a certain recursive pattern going on over here, right? So the idea is to simply store the results of subproblems. So where's the subproblem here? It's when you choose one item and then resolve the problem. The problem that you're resolving, so when person B picked item 1, he's going to solve the same problem with items going from 2 till 6. So this is the subproblem. You store the results of the subproblem so that we do not have to recompute them later on, right? So for that, I'm going to use C++. I'm going to open VS Code over here. It's okay, you can use any editor you want. I'm a fan of VS Code. And let's solve this problem that we had over here. So for those items corresponding to the given values and weights. So if you're not a fan of programming or dynamic programming, it's okay. You can fast forward, go to the convex optimization part, it's okay. For those that are a fan of programming, you're welcome to watch this part. So I'll first include the C++ library and I'll open a main. I'll define an array of values, which will be 175 through 200, and an array of weights, which will be 10 through 20. The total capacity of my knapsack will be 20. And the total number of items is just size occupied by the array V over the size of the first entry of the V. I'll call knapsack, passing it total capacity, the array of weights, array of values, and the total number of items, and that's it. Run. As you can see, there's an error because we didn't implement the knapsack, so let's do that. Over here, I'll go ahead and define void knapsack, pass it W, the array of weights, the array of values, and the total number of items. So since we're taking a dynamic programming approach, we're going to build a 2D table, T, that will be filled up from bottom up. Okay, for that I'm going to define a 2D loop. The table will be of size n plus 1, w plus 1, and we're going to argue on some cases. So the base case is when we're at the first row or column. For that, I'll just give it a value of 0. Else, if the weight of the ith entry is less than j, then I'll just return the max of 2 cases. The first case is when we don't add this item, right? Or it's when you do add this item as such. Now in any other case, you'll just take the preceding value. Now as you can see, it's yelling at me over here telling me identifier max is undefined. So let's go ahead and define it. We'll want to return an integer, which is the max of 2 integers. So we'll just return the max as such. This is shorthand notation of returning the max of 2 integers. Okay, so let's continue the flow over here. At this point of the code, we have the total value, which is stored in the last entry of the table, right? So we'll print total value, and the knapsack is equal to %d, then go to another line and print the total value, right? And now we can also define the remaining weight of the knapsack. So to find the items that we pick, we're going to run a backward loop given the following conditions. So if my total value is the one sitting at this entry, I'll just continue the flow. Else, we have found the item in the knapsack that has a weight in the ith entry of W. Then we're going to have to reduce the total value for the value of the ith item. And also, we're going to have to reduce the remaining weight. Last but not least, let's print a statement saying, go to a new line first of all, remaining weight is percentage D, remaining weight. Okay, all looks good. Now this I isn't defined because we only defined it in the loop. So I'll go ahead and type in again int as such. Run, and as you can see, this is the output. It's telling me that the total value in the knapsack is 275, which we got over here. And the items that we picked are items 1, 2, and 5, corresponding to weights 1, 9, and 10. 1, 9, and 10. The remaining weight is 0 because 1, 9, and 10 sum up to 20, which is exactly equal to the capacity of the knapsack. Hence, we don't have any more space, so a remaining weight of 0. So this is how you get the job done using dynamic programming in C++. So enough with dynamic programming, let's talk about the convex part of this problem. So this problem is not convex by nature because it looks convex, but it's only due to one thing, because of this condition or this constraint. If this were eliminated, then this problem is not only convex, but it's also a linear program. Why? Because it looks like this. So if I define a vector v of values, v1 down to vn transpose, and a vector of weights, w1 down to wn transpose, and a vector of decision variables, x1 down to xn transpose, then the problem looks like this. So you'd want to maximize a v transpose x subject to one inequality constraint, which is w transpose x less than w. This problem as such is LP, which is convex. However, if I come and add the constraint that xi falls in 0 and 1, it's not convex. So only this aspect is an LP, right? This problem is called an integer program, right? Because it's a linear program plus an integer constraint on your variables. Now, when some of your variables are integers and others are allowed to move in R, it's called a mixed integer linear program. Mixed because we're mixing between real and integers. So if you wish, this is the set of all MILPs, and inside it lies IPs, that stands for integer programming. So IP is integer programming, MILP is mixed integer linear programs. Oh, and by the way, binary integer programming is also a specific case of integer programming. So BPs lie here. The problem that we have over here is a BP, in fact. Now BP, why? Because not only is your x an integer, but it's only restricted to binary values, 0 or 1. We're going to look at this problem as an MILP, and we're going to profit from a very important function in MATLAB called int linprog. I'll type in help. This is the documentation. For a better description, you can open help and read about the MILP. So we're minimizing f transpose x. Oh, and by the way, this could be written as a minimization easily. All you have to do is include a minus sign here, remove the maximize, and type in minimize. So back here, we're minimizing f transpose x. So my f here is the v over here, subject to my x's are integers. Okay, there is 0 and 1. And you've got an equality constraint, which we obviously don't have over here, and an inequality constraint, right? Ax less than b. My a over here is the w transpose, and my b is just the uppercase w, right? You can read more about this function over here. So f is my objective, it's a vector. Int con is a vector of integer constraints. You can pass a and b. A equality and b equality will leave them empty, and lower bound, upper bound will just, bound our x to be between 0 and 1, because it will either be 0 or 1. So let's do this. So I'll open a new script, call it Knapsack. I'll clear my workspace, and I've got 6 items with values equal to 175, 90, 20, 50, 10, and 200, just as we had over here. And the weights, I'll just copy them into a vector called w. The maximum weight is w, which is 20. So my solution x will be generated by int linprog, which solves an MILP with objective f. I'll pass an int con, matrix A, vector b, matrix AEQ, vector BEQ, standing for equality constraints. and lower bound and upper bound. Now let's fill those quantities over here. So my f was just my minus v, y minus, because it's a minimize, minus v transpose. So I'll take in minus v, right, to be my f. So it's minus v, and con I'll just take it 1 till n. A is w, why w? Because it's an a. If those were column vectors, then this is a w transpose, and this is a v transpose, right? And my b is just uppercase w. My lower bound is zeros, and my upper bound is 1. If we run this, we've got an error here saying, what is AEQ? Oh, we forgot about that. We forgot about AEQ and BEQ. Well, they're just empty. We don't have equality constraints. Run. An optimal solution is found. Well, let's print it. Remove the semicolon, and there you go. So 1 in the first entry, 1 in the second entry, and 1 in the fifth entry. So in other words, we're picking the first, second, and fifth item as individual B solved the problem. So individual B chose the optimal solution of the problem. So that's it for the 0-1 knapsack problem. That's all you need to know. This is how easy it is. Of course, there's many other variations on the knapsack problem, such as the fractional knapsack problem, where you're allowed to pick a fraction of item A, that is, you're allowed to cut it into a fraction, take a portion of it. You're allowed to take a portion of any other item that you wish. That said, your x is no longer a binary variable, it's a continuous variable, varying from 0 to 1, and hence you will get a linear program, as simple as that. You've got other types of knapsack problems, such as the bounded knapsack problem, where you say, oh, my xi's are between 0 and an upper threshold, let's say C, where C reflects the number of copies of each item, right? You're allowed to take copies of item 1. So let's say item 1 is present, let's say with 20 copies. Well, how many copies could you pick from each item such that you maximize your total value in a finite or in a given knapsack that has a certain capacity, right? You also got the unbounded knapsack problem, that is, there's infinite copies of each item, and you ask yourself the same question. What is the best combination of items I could pick, including their copies, such as they fit in my knapsack? So if you're interested in the fractional knapsack or the bounded and unbounded knapsack, those are variations of the original 0-1 knapsack problem. If you're interested in any other variation, please leave a comment in the comment section below. I'll make sure I'll publish a lecture on that. If you found this lecture beneficial, please like the video, subscribe to the channel so that this channel keeps on progressing and growing bigger and bigger. Thank you so much, and I'll see you in future lectures.